USACO Summit. So the event is happening right now, and we thank you for your patience while we waited for people to join. But now the wait is over, and if you can, feel free to turn on your camera if possible, so we can see each other. So first of all, welcome to this event. Here today, we're just going to go over what is USACO and why we go and participate in USACO, and then we're going to do some preparations for the upcoming competitions that's going to happen in the coming 2 months. All right, so first of all, what is USACO, right? USACO stands for USA Computing Olympiad, and it's an individual problem solving and coding competition, and it's held during the months of December to April, and it held 4 times throughout this school year. And you have around 3 to 5 hours to complete 3 problems with the max score of 1,000. And each problem was in the same amount of points. Problems can be submitted multiple times, but the final attempt is what will be counted and reviewed. And you will be tested on your algorithm thinking and problem solving skills. You can complete this in many languages, including C, C++, Java, and Python. But most commonly used are C++ and Java. So in USACO, there are 4 tiers. One is bronze, which it basically shows that you have basic understanding in the fundamentals of programming, and you have decent problem solving skills. And then if you pass that, you can reach silver, which that means you demonstrate somewhat of an understanding in data structures and the basics of algorithms. If you can even advance to past silver, you can go to gold, which it shows you have the ability to solve complicated algorithms and advanced data structures with somewhat of a strong math background. And then if you're really good, you're a mastery, then you can reach platinum. And here you have advanced data structures and algorithms and combinatorics, and you demonstrate amazing computational thinking skills. As you know, App-In Club, we focus on app creation, but USACO is an event that if people are interested, feel free to participate. Because in this competition, you can demonstrate to any application, oh, I have good combinatoric skills, I have good computational thinking skills, right? Since when you apply for any program, college or summer camp, they're gonna ask you what do you have to prove that you're good, right? And USACO is one of those competitions, aside from the hackathons that we talked about 2 weeks ago, if you guys were in the Metro Hacks event. So something that people wonder is why compete in USACO? Apart from the reason I just said, another reason is the experience, right? Usually in competitions, you need to have many experience so you can actually be successful in it. So therefore, definitely try USACO at a young age, even if you're just not gonna do that well. Even if you can pass bronze, that's still good because you have many tries, right? You have 4 tries each year, and then assuming you're freshman in high school, then that means you have 4 times 4, right? 16. And then, so yeah, definitely experience is a big part. The second one, I mean, look, if you can get to even bronze, it's still an achievement, right? You can still write it on your resume or whatever. And then if you do well, you can be promoted to higher divisions and gain local and national recognitions during competitions. And if you're really good, you do really well in the platinum, you might even get selected into the national team for IOI. And also, since we're all passionate, innovative young individuals here, fun is a big part of this competitions. We have to to develop a passion for a certain subject, in this case, computer science. We need to have a passion for solving problems, because coding is not just about they gave you a prompt and you just code for it. A lot of people have the concept of coding for websites, right? Yeah, that's one part of coding. But another thing is how do you make your code better, right? Because right now, say if you use ChatGPT, everyone heard about ChatGPT right now, right? If you use ChatGPT, yeah, you can write code, but guess what? It's bad. It's clunky. So we have to refine our code to make it to be smarter. Not technically, but the code has to be runs faster and more efficient. And how do we do that? Through algorithms and learning these new algorithms. And so that's why here it's very fun and like very interactive to learn about these unique ways to solve problems. Not just a check. This is the third time, but just like make sure you mute yourself so we don't disrupt anyone else in the meeting. Now, after I talked about the introduction to USACO, let's talk about our speaker here. So everyone welcome Adrish Kar. He is a passionate senior in American high school who has a passion for computer science. He enjoys exploring like the many aspects of computer science, including like algorithm, computer network, AI, and robotics. Adrish is pretty accomplished as a competitive programmer, who has honed his analytical and programming skills through participating in many competitions, including USACO, where he currently holds a gold level. And aside from his coding skills, he's extremely good at like math and other extracurricular activities. And he's the current president of the CCC Club, which is the Competitive Computing Club. So let's have Adrish take it from here to let us walk through some problems. So Adrish, your turn.
Yeah, sure. Okay, yeah, so I guess thank you for the introduction, Tony. And so first of all, I want to thank you, Tony, and the App-In team for hosting this event and having me here and letting me speak in this event. I think this will be really beneficial for competitors of all levels, whether you have experience or not. So thank you for that. And I guess for a bit more context, I'm currently, as Tony said, in the gold level. I promoted in the US Open 2022 contest, but prior to that, I was stuck in silver for like one contest season. But without further ado, I guess I can move on to my presentation. Can you see my screen?
Yeah.
Okay. So I guess I think you can still hear me, right? Okay, cool. So I guess Tony kind of talked about what USACO is and why you should do competitive programming. So I guess the next thing would be to naturally talk about resources for USACO. So here just you can see like are some resources to prepare for USACO. Just going down the list, we have USACO Guide. I'm sure most of you attending have probably already used this. But USACO Guide provides a really good curriculum for competitive programming, and it links problems under topics, which themselves are listed under divisions, them being bronze, silver, gold, platinum, and advanced, I believe. And it's a really good resource for preparing for USACO. And then Code Forces, it's good, but it's only good after you've completed all the USACO problems on the contest website. So USACO Guide and the past contest problems listed under the usaco.org website using conjunction are really good for preparation. And also, this is from one of the videos from the creators of USACO Guide. But the idea behind using both of these resources to prepare for USACO is that you use USACO Guide to sort of build a really strong foundation on your algorithms and data structure knowledge prior to tackling all the old problems on the usaco.org website, and sort of do like a blind topic blind practice on the website. And here are some other resources. I haven't used this website much, but I've heard that it has a pretty nice list for like all the algorithms and data structures required for competitive programming. These are some YouTube channels that I use for USACO. This channel in particular is also can be used for like other Olympiads. And I think Carrara also has like a Discord channel which you can check out. And then I guess other than YouTube channels and these resources, there's the unofficial USACO Discord server, which is really helpful because it has like, I think the past IOI members are members of like the Discord server. And there's also a lot of other like really accomplished people on the unofficial USACO Discord server that you can ask for help on problems. And it also has more resources than the ones listed here. And I guess I've also linked the Discord server link for the Competitive Computing Club, which I'm currently the president of. We usually have meetings every Wednesday from 4 p.m. to 5 p.m. In which we have breakout sessions for bronze and silver. And I guess we also are planning on having a contest in the near future. So if you're interested, please consider joining. But yeah, these are just some resources for USACO and competitive programming in general. And I guess now I'll just provide some contest tips. So after this, I'm going to walk through 3 problems. But prior to that, I'll just walk through some contest tips. Okay, so this is the competition schedule for reference. And so when you're practicing for USACO, consistency is really key. Obviously, you might not be able to practice every day of the week consistently, but try to practice as much as you can. These are just some time estimates I put. Obviously, you can like alternate weekdays and like do most of your practice on the weekends or vice versa. But you should remember to prioritize quality over quantity. Like if you have other commitments on certain days, you should prioritize working on USACO on other days when your mind is like fresher and you have more time to commit. Those are just some like basic tips in just general preparation. And then obviously you should take advantage of breaks like Thanksgiving break or winter break. I know until the next contest, which is like US Open, we don't have any breaks other than spring break, which is like after the US Open. But for those of you who are eligible to compete next year in the following season, you can use summer break definitely to prepare for USACO pretty extensively. And then I guess another general sort of practice strategy would be to learn topics and concepts completely prior to applying it to problems. Like you don't want to waste problems. Like if you don't know like a particular algorithm, or if you haven't learned like a topic exhaustively enough. And you should attempt to use problems usefully. What I mean when I say that is like, you should focus on trying to solve and get as much of the solution as you can by yourself prior to like looking at the solution. So you should really focus on time spent making no progress when solving a problem in order to gauge when to look at the solution. And typically people say about 15 minutes, like if you've been working on a problem and it's been 15 minutes that you've made no progress, you should just look at the solution and just learn and absorb as much of that knowledge as possible. But I think maybe 15 to 30 minutes of making no progress is good. And this is applicable more to like the more difficult problems. You should implement the editorial solutions after reading them. So after, let's say you've looked at and read like the solution to like a USACO problem, you should just try to code it up like all by yourself, without looking at the solution. And I guess I touched on this earlier, but a great way to sort of get into USACO and like also like hone your analytical skills, algorithmic problem solving skills would be to just do the old contest problems on the USACO webpage. And if you've done all of the problems, there's all the problems listed from 2014 to I think the present day, or probably even earlier than that. You can do problems harder than your own level. And so that was like pre-contest. There's sort of two sort of phases, I guess, pre-contest and during contest and post-contest. So I guess that makes it 3. But so during the contest, these are some tips. First of all, you should read all questions and sort each problem by difficulty. So typically, one of the mistakes that it's really easy to make is if you look at the first problem, let's say you hit that start contest button, you look at the first problem and you get really excited and you want to like code up that problem immediately. You shouldn't really do that because one, you should at least look at the other problems and because they might be easier. And two, you might realize like 10 minutes down the line that the solution that you were so excited about was like wrong. The approach was wrong. So you should read all the questions first and then sort by difficulty prior to diving into any of the problems. And that's a pretty important sort of point. After that, I guess a bit about how to like tackle each of the individual problems that you see. First, you want to do like the sample test case by hand. For those of you who are like not familiar with USACO, they give a sample test case and a sample output. And then the test cases that your program is graded on are like not known to you, but they do give like one sample test case. So you should do the sample test case of each problem by hand first, and you should also try to think about 6 to 7 other test cases and try to find patterns, which is a really helpful tactic in order to crack these really hard algorithm and data structure problems. And I guess the wording over here on the third bullet point is kind of ambiguous, but these are 2 separate additional tactics that you can use. First one would be the time complexity gauge. So typically in almost all basically competitive programming contests that you'll find that they'll give you bounds. And you can use these bounds for like certain variables to gauge the time complexity of your algorithm. And this is really, really helpful. Let's say like n is 10 to the power 5, then you know that you can't do like an O of n squared algorithm. That's just an example, but you can kind of use that sort of to advise your solution. And the second thing on this bullet point is the topic list. So before you start like a contest, you should try to internalize all of the algorithms and data structures that you know. Off the top of my head, I can just like list a few. Let's see. Or I guess I can just say it. So some of them would be prefix sums, BFS, DFS, graph traversal, difference arrays, data structures, which include vectors, stacks, queues, priority queues, DQs. Binary search is also really, really important for bronze. Upper bound and lower bound are also included, custom sorting. So you should try to like have this already internalized in your head before going into a contest so that you can like kind of pick one of these like topics to try to attack the problem during the contest. And after this, I guess time management is also another crucial aspect of competitive programming. In the initial moments of the contest, you don't want to spend more than 30 minutes on one problem. So typically, we start a coding problem and we are like, you tend to spend like an hour on it. Maybe like you're coding or trying to debug your code for like a problem. This is like a mistake. You should at least try to spend a decent amount of time on each problem prior to like going and tackling one particular problem for an extended duration of time. And then for the final moments of the contest, you should attempt to get partial tasks. So in the initial moments of the contest, you shouldn't do more than 30 minutes on one problem, but you should try to like have write code that solves the entire problem and not like partial tasks. And then for the final moments of the contest, so probably 30 minutes, you should try to like just get all the partial tests that you can. And I guess some things on here that are left, the journal log approach, I personally haven't used this, but I believe it's been suggested by finalists such as, I think this resource over here, I think Ria Aurora, she suggested like a journal log approach, which has helped a lot of like contestants. Essentially, the idea is that you have a sort of journal log in which every 15 minutes you note down what you did in the past 15 minutes. So it would look something like this. So, okay, yeah. So you have activity, and then time. So let's say in the first 15 minutes, you write down read problem 1. And then maybe in like the second 15 minutes, I'm just going intervals of 15, you attempted to code it. And you might be thinking, oh, what does this do? Like, how does it help me during the contest? So the reason for doing this is to kind of see how you're spending time, like visually. Like usually, as I said earlier, it's really easy to get carried away by like one problem, but let's say you like note down how much time you're spending on one problem, and you're doing this every 15 minutes. You can see that if you've like, let's say you've in the 45th minute, you're still like, I don't know, code, debug, problem 1. And then it's been like an hour. Debug, problem 1. So usually if you don't have this sort of diagram or like this sort of way of keeping track of your time, you have no idea of how much time you spent. But if you see that you've spent like 30 minutes, you can actually stop early. So instead of like continuing to do this like for 45 minutes and an hour, you can actually draw the line over here and then switch to problem 2. So this is like a sort of helpful strategy that you guys can use while doing the contest. I personally haven't used it too much for myself, but it is a really good way to do your time management. And then I guess the last bullet point on here is stress testing. So stress testing, it's not frequent. You don't do this frequently during USACO. At least I haven't done it and been successful, but essentially it's when instead of like manually generating test cases and like doing them and like working through and trying to find patterns, you have a program that generates random inputs, and you have like a brute force algorithm that is like a worse time complexity than the intended solution. And then you have your optimized code, which is the code you'll be submitting to the grading server. And you essentially combine those two programs and compare inputs to identify cases in which your code doesn't work. So I believe there's like an article, or you can also ask around on the unofficial USACO Discord server, but this is a pretty common strategy for competitive programming, especially I think in Code Forces and other such competitive programming contests. So I think that's pretty much it for the contest tips. I guess now I'll be walking through some problems. Let me see. Okay, so I guess the first problem that I'll be walking through is the USACO 2023 January contest bronze problem 3, mu operations. So essentially, this problem, we have Q strings, each comprised of the characters M and O. And essentially, our job is to determine that whether for each string listed in the sample input, whether it's possible to use these two operations repeatedly to arrive at this ending string moo or moo. And so if I scroll down, you can see like the sample output. For the last one, obviously there's like 0 operations. Oh, and it's not whether it's possible, but like the minimum number of operations. So obviously for this one, it's not possible to arrive at the ending string moo. For this string over here, it's already moo, so there's 0 additional operations. And for this one, they've listed the operations that can be performed. So replacing the last character with O, deleting and repeatedly deleting the first character. So that will get you to this desired string at the end in 4 operations. And as for the character operations themselves, as the problem states, you can either remove the first or last digit, and that counts as, or not digit, but character, and that counts as one operation, or you can toggle the first or last character. So O becomes M, or M becomes O. Okay, so I guess now that we have a basic understanding of the problem statement, oh yeah, so this is what I meant by subtasks earlier. So over here for inputs 2 to 4, you can see that the string length is guaranteed to be at most 3. So let's say you didn't get the overall like implementation, or the overall like the final solution, the desired solution. You can still get like test cases 2 to 4. So you can probably get 4 out of 11 if you wanted like partial credit. So, okay, so going back to what I was saying, I will now shift to my whiteboard. Can you still see my screen? Or can you see like a blank screen? Okay, cool. So now let's start with like a sample string like this. So I guess the most evident part about this is that we have, once again, obviously 2 operations. I'll just list them again. And then okay, so we want to end up at MOO. Okay, so with this problem, obviously the desired string length at the end, the first step would be to notice that the desired string length is 3 at the end. And if your string has a length that's greater than 3, you need to use this like second operation in order to make it so that the final length is 3. So, and then I guess another observation that follows from that is that if you want to remove the first or last character, and if you want to remove any character in general, you don't want to toggle it beforehand, because it doesn't make sense to toggle a character if you're going to remove it ultimately at the end anyway. So I guess for this sample test case, if we do this by hand, we can delete the first character repeatedly. And after we've done 2 operations of deleting the first character, we can do 2 more operations of deleting the last character. And then we can toggle this last character over here. So that's one more operation. So we can get to this desired string MOO in 5 operations. So that's just one case. And so what you end up seeing is that you ultimately, in order to get to MOO, you end up in one of the n-2 consecutive 3-character positions along the string. So n is the length of the string in this case. And this is our string over here. So n is the length of the string. And you can actually see that you end up in either this sequence of 3 characters, or this sequence of 3 characters, this sequence of 3 characters, this sequence of 3 characters, etc. So actually it's kind of cluttered, so I'll just erase some stuff. And then so knowing this, we can iterate through the entire string for each of the n-2 positions. So the pseudocode looks something like this. Oh, my bad. It's supposed to be n-3 inclusive. We can check how many operations it will take to transform each contiguous substring of length 3 from I. How many operations it would take to transform that string to MOO. And we can actually do this in Vent. So we can do like a bit of pre-computation. So for each possible substring of length 3, we can like sort of enumerate and like map it to how many additional operations it would take. So I guess I can erase the right side. I think the operations, we all have a basic understanding of that. If I have MMM, then is there any way to transform it to MOO using the aforementioned operations? There is not. If I have the string MMO, is there a way to transform it to the string MOO at the end? There is not again. What if I have MOM? Over here, we can see that it takes one additional operation to transform or toggle this. So this takes one additional operation. For the string MOO, it takes 0 additional operations. For the string, let's see, OOO, we can actually do this in also one additional operation. Let's see. And then for OMO, this is actually not possible. So after like enumerating through, like, I guess there should be 8 of these because 2 to the third is 8. So I have like 6 of them here so far, but you can kind of see that if the middle character is an M, then it's not possible to transform the string into MOO because there's no operation to transform the middle string or middle character. So in code, what you can do is sort of have like a tree map or a hash map of each like string, and map it to like the minimum number of operations it would take to transform it into MOO. So for the ones that aren't possible, you don't have to include them as keys in the hash map or the tree map. But for the ones that are possible, like MOM, MOO, OOO, essentially all the substrings that don't have a length of, or don't have like the middle character as M, you can like map them to the minimum number of operations needed. And so once you have this, while you're iterating, the answer would then be, you can have like a running minimum. So like the answer you initially set to like, I don't know, some like large number, 1E9 or something like that. Then your answer would be the minimum of the current answer. Let me rewrite that. The minimum of the current answer plus or comma the substring, whatever substring that is at this position I, and you would want to access this using like the map over here. So this, the value over here, you would add this to the number of characters in the string minus 3. So it's kind of messy over here, but you would add this to n minus 3, because that's the number of operations needed to delete the other characters. So I guess to clearly outline our solution, I'll just clear all drawings. We have 4 int I goes from 0 to n minus 3 inclusive. We set answer, we initially set answer to like a max of 1E9. And then we have answer equals minimum of answer and answer, and then map of string of substring I plus 3. And then this plus n minus 3. And then, so this would be the answer. And then obviously at the end, you just output answer. And this is just for like one of the strings. So you can probably have like a solve function that does this. Okay, so that's pretty much like the solution for that problem. I guess we can probably move on to the next one. Okay, so can you see my screen again? Okay, cool. So for this problem is subset equality, which was problem 2 of the USACO 2022 US Open Contest Silver. In this problem, we have 2 strings of length at most 10 to the 5, consisting of the lowercase English letters A through R. So I guess at first, when I saw this problem, I think this was the contest I promoted in. I saw A through R, so I don't know if that's like anything significant, but it may indicate that since there are only 18 letters separating A and R, that it's probably significant to the time complexity and coming up with the final solution. But I don't know why they actually had only going from A to R and not like A to Z, but I guess doesn't matter. Going back to the problem statement, the first line has S, which is one of the strings, and the second line contains the second string, which is denoted by T. And we have a series of Q queries, and Q is in the range 1 and 10 to the 5. It's the maximum value it could be is 10 to the 5. And we're asked when each of these Q queries, we're given a subset of letters that are present in each of the strings, and we're asked to output a string that tells us for each of these Q queries whether these two strings are equal if they're restricted by the letters in the subsets. So I guess that was a kind of mouthful. It's easier if we see an example in action. So let me see if I can annotate directly on this. Okay, I guess I'll just go directly to the whiteboard. Okay, so okay, cool. So in this problem, once again, we have Q queries. Q is in the range 1, 10 to the 5. And we have the two initial strings that were given in the sample input. And this is Q, so this was 4. And the Q queries in the sample input at least were as follows. Okay. So let's just work on the first query. If we restrict each of these strings to just the characters A, are they equal? So for the first string, we'd have to restrict this to this string becomes just AA. Essentially, we're just taking all the characters that are A are included in this subset, and we're just writing them from left to right. The same thing we can do for the second string. So AA once again. And so when we compare these, obviously these are equal. So the first character in our output would just be Y, which is like, yes, they're equal. Okay, so that's good. What about the second one? So for AC, if we restrict those two strings to characters A and C, then we have AAC for the first one and CAA for the second one. And we can see that these strings are not equal. So the second letter in our output string would be N. So YN and et cetera and et cetera. So ABD, if we just focus on this third one, ABD, we have AABD, and also the second one, AABD. So the third letter would be Y, and then the last letter, we can obviously see that this is not true. So that's essentially the essence of the problem. So I guess to sort of break down my thought process when seeing this, first of all, I guess I noticed that it's not possible to do to have like a algorithm of time complexity O of Q times the length of the string, or the max length of the string, I should say, but essentially so this time complexity does not work because Q can go up to 10 to the 5, and the maximum length of the string can be, or each of the strings can be 10 to the 5 as well. So this clearly will not work because 10 to the 5 times 10 to the 5 is just 10 to the 10, and this is greater than 5 times 10 to the 8, which is typically like the number of operations per second that the grading server can handle for USACO. So this algorithm won't work. So this is essentially indicative that we have to do some pre-processing in advance prior to going over like the queries, prior to inputting them. So at first, I actually thought about hashing, which is essentially like translating these strings into like a number that we can compare to the second string. So like I was thinking, let's say in base 10 or something, I could like hash each of the letters, each of the substrings of the letters into like some representation, where if I had like a substring that was given, I would be able to like immediately compare the hashes of each of the subsets between the two strings. But after thinking about it for like 5 minutes or so, I realized that this was infeasible because one, the base is like 10 to the 5. So I'd have like essentially a hash of length 10 to the 5, like 1 followed by like 10 to the 5 zeros, which is like not feasible. And the second reason was because these positions, when you take them by their subsets, their positions change. So if you had the substring A, or the subset A, I should say, the positions of these two A's in the first string, when restricted to this subset, would just be 0 and 1 if you're using zero-based indexing. But if you consider this subset, the second one, AC, then or I guess a better example was the second string. So if I restricted to the subset A, then the positions would be 2 or 1 and 2. If I restricted to A and C, the subsets, the positions would be 2 and 3, but for A, it's actually 0 and 1. So these two positions are not the same. So like that's why hashing, I ruled that out. So that's one thing that's pretty important. You need to like rule out approaches or solutions pretty quickly. And so the way I came up with the actual like the final solution, it's a bit convoluted, but I found it to be intuitive for myself. But I think if you just write out the strings, you notice that if you're given like a subset, say AC, then these two strings can only be equal if the corresponding letters are in like the same position. So the first letter I have in this subset is A. So if I draw like these two lines, the first letter in the first occurrence of A in the first string is connected to the first occurrence of A in the second string. And if I had like another A, let's say, this is kind of what I envisioned. So let's see. So essentially, yeah, I just like drew these lines when like doing the problem. So essentially what's happening is that each corresponding letter is in the first string is connecting to each corresponding string or character in the second string. And so the first occurrence of A in the first string is connected to the first occurrence of A in the second string, and so on and so forth. And so I noticed that if we take the second sort of letter and do the same thing, so first occurrence of C in the first string connected to the second occurrence or the first occurrence in the second string, we can see that this subset fails because these lines intersect. over here. So even if there's like one intersection, that means that these strings are not equal. Essentially, that the letters, the corresponding positions of the letters are not equal in both of the strings. So if I have like another example, probably we can have let's see. Let's say the substring was D, DA. Let's do AD. So if I do this, then I can see that none of the lines intersect. And so I have, for the first string, I have ADA. For the second string, I have ADA as well. So these strings are equal. But at the second that the positions don't match up of like the letters, these strings are not equal and restricted to the subsets. So the next step from here would be to realize that instead of focusing on the entire subset of letters, so let's say if I had like a subset with more than 2 letters, let's say AD, or probably better is ACD, I can focus on each pair in the subset rather than focusing on the entirety of the letters in the subset. So I can check pairwise whether A and C, if any of the lines cross, whether A and D, any of the lines cross, or C and D, any of the lines cross, instead of drawing all these lines all at once and checking whether there's at least one intersection in the entire, like one including all letters. So obviously we can't do this when doing when like going over like all the queries themselves, because we need to do like pre-processing in advance. So the best solution, like the step after this, would be to pre-compute for all letters, all pairs of letters, that is to say.
I'm not sure I understand.
Oh.
Is there something else I can help with?
I think that was my Siri going off. My bad. Okay, anyways, getting back to the question. Okay, so yeah, we could create like a matrix between all pairs of letters. And in this Boolean matrix, we can store the value true or false, which indicates essentially whether, if we include A and B, or A and C, each of these pairs of letters, whether the strings are equal or they're not equal. So in this case, for when doing pre-processing for like all the strings, we can see that ACD is, or AD is equal. So I can put this as true. AC is also equal. AB is, let's see. AB is not equal. If I add like another A over here. And I believe I think we like covered all the test cases that we needed to, but essentially we have this like matrix already created in advance. And essentially, while we iterate over like the queries, A, AC, ABD, we can actually, instead of including all these letters, we can iterate through, we can have like 2 sort of pointers. We can iterate through all pairs and check whether like the value, if one of these values is false, then we know that the entire query evaluates to false. So that's essentially the solution. So and the overall time complexity for this would just be well, O of the number of letters, which is like 18, I guess, squared. So I'll denote that by L squared plus Q times, let's see, 10, well, the subset, the letters of the subset squared again. Yeah. So this is like basically like a constant factor. So overall, the time complexity would technically just be O of Q. So this runs in time. So whenever you realize that you can't do like an O of n squared or a higher polynomial time complexity for your algorithm, you should try to do some pre-computation, or like try to like see if you can do any pre-computation. So I guess that's it for that problem. I did have, I guess, like another problem that I wanted to go over, but Tony, do you think that we're hitting like any time constraints?
No, we have time. The event is like supposed to be around 1 hour 40 minutes, so it's fine.
Okay, cool. Sure. So I guess I can move on to the next problem. Let me see if we can stop sharing. Okay, you can see my screen again, right? Okay, cool. So this question, this was the January 2022 contest for silver. And this question, serial 2, it was pretty difficult for this division. I remember a lot of people like complained about it. But I guess we can just look at the problem statement now. So in this question, we have n cows, which have a favorite cereal and a second favorite cereal. And we also have m different types of cereal. And essentially the cows, they're in some permutation that we have to figure out. And they follow the following procedure, or the following process. If the box of the favorite cereal is available, they take it and leave. Otherwise, if the second favorite cereal is available, then they take that and leave. But if neither the first or second favorite cereals are available, they just leave with that give out. They will move with disappointment and leave without taking any cereal. So our task is to find the minimum number of cows that go hungry, and we're also supposed to find the permutation of the n cows that achieves this minimum. So this sort of line over here, this is what made it seem like really daunting, because in addition to the minimum number of cows, we're also supposed to find the permutation. So that killed a lot of motivation in this contest. And I guess looking at the sample input and output, we can go through this on the whiteboard, but notice that they have some afternotes over here. I don't know if they, oh yeah, they do have that. But it's sometimes helpful to look at what they say over here, because as is the case with this problem, this actually turns out to be pretty helpful, the notes that they leave over here. So I guess I'll like shift back to my whiteboard. Okay. So I'll list all the constants given in the problem. So the sample input was 8, 10, and the first line had n and m. So there are, in this sample input, there are n different n cows. and 10 of the 10 like different types of cereal. And each of these n cows has a list of basically a 2-element list of preferences. So we have 1 likes 2, like this is the first favorite cereal and this is the second favorite cereal. So I'll just rewrite it over here. Okay. Okay. So you can kind of notice this, but they actually mentioned this in the after notes for the test case, the sample test case. You can kind of see that the cereals like over here, and the cereals in this latter portion of the test case, they don't share any common cereal. So we can kind of focus on these two sort of sections independently and determine like the optimal permutation independently. Now this is like really hard to like realize, but I guess even if you didn't realize it in the sample input, you could probably make one test case of your own and realize it then. So if we just go through this, right? Let's say we have the ordering 1, 2, 3. Then for cow one sees that this first cereal is available, 2, and they take cereal 2. So I'll actually have okay, let me see. This is permutation. And this is the list of cereals that are available. So far we have 1, 2, 3 are available. I'll actually erase this. So once cow 1 picks the number 2, cereal 2 is not available anymore. Then according to the permutation, cow 2 arrives, and cow 2's favorite cereal is 3. So 3 is taken. And then finally cow 3 arrives, and we see that cow 3 likes or prefers cereal 2. So cereal 2 is actually taken. So for this permutation, this is actually not an optimal permutation because one cow, which is cow 3, will leave and they will go hungry. So this is not an optimal permutation. Whereas, yes, I can pull up the problem for reference. Okay. Whereas for this permutation, 1, 3, let's switch this up. 1, 3, 2. And I'll like restore the list of available cereals. So in this case, cow 1 arrives, they pick the second cereal. Cow 2 arrives, pick the third cereal, or actually, that's exactly not what we wanted to do. Cow 3 arrives, and they pick, I guess I'm gonna actually change this to 1. I think that's what it was in the original one. Sorry about that. Cow 3 arrives, they pick the first one. And then cow 2 arrives and they're able to pick the third one. So this is an example of like an optimal permutation. Yeah, I think this was 1. So I guess one thing that we may attempt to think of when like looking or like when trying to come up with a solution would be to kind of have like a greedy approach. At least that's what I thought of when I was taking this contest. Some sort of like greedy approach for like the permutations, and maybe only working on the permutation. So there's a total of like n factorial permutations of the entire set of cows. But maybe we can try to like prune this to a smaller set. That's one of the ideas that you may have. But this doesn't exactly work out. There isn't like a metric to prune the permutations based off of, or at least there isn't like an obvious way. So I guess after maybe thinking for some time, you can probably rule out this way to solve the problem. Okay, so if this way doesn't work, then what else can we do? So I guess at this point of time in the 2022 contest or 2021 to 2022 season, they actually, I can't remember if it was the contest season before or this one, but they introduced graph problems. And there were quite a few graph problems in the January contest, the February contest, and even the US Open contest for silver at least. So prior to then, they didn't have that many occurrences of like graph theoretical sort of problems. But it's nice that they actually added it. So whenever, I guess a general tip is whenever you have a pair of numbers in the input, it is worthwhile to sort of think of like a graph theoretical approach. So I guess if the ad hoc solution doesn't work, or like the greedy method solution doesn't work, you can think of try to like construct a graph using the input. So the step after this would be to try to represent the input as a graph. So there are actually like a number of graphs you could construct, right? And for those of you who are maybe not familiar with a graph, essentially what it is it's like a set of nodes and vertices. Or sorry, nodes and edges, nodes connected by edges. So one possible graph that we might construct using the sample input is from mapping the cows to their preferred cereals. So 1 goes to 2 and 1, 2 goes to 3 and 4, 3 goes to 1 and 3. That's like one possible graph that you may come up with. Another possible graph that you could sort of envision using this input would be to connect the first preference cereal to the second preference cereal for each cow. So 2 to 1, 3 to 4, 1 to 3. And from these, like maybe you might construct 4 or 5 or like many such types of graphs, and then you might try to narrow it down to see which possible like graph configuration is the most optimal or makes like the most sense given the objective of the problem that we're trying to solve. So for this one, you can kind of see it, but this approach of like constructing the graph is kind of pointless because the vertices over here, they represent like different things. So on one end, there's the node, which is like on one end, there's like the type of the cow number, and then on the other end, there are the preferred cereals. So it doesn't make sense for the vertices to represent two sort of different things. And you can't like, this 2 is not the same thing as this 2 because it's like the cow number. So we can rule this this way of like approaching and constructing the graph out pretty easily or pretty early on. What is pretty interesting though is when you have like pairs of inputs, I think this also appeared in the US Open contest. You can connect this approach over here actually works out quite well. So you can actually construct a tree or a graph, I should say. So I'll like redraw it over here, 2 to 1, 3 to 4, and 1 to 3. And you can sort of think about labeling the vertices as the serials, which we had already established earlier. Since we've labeled the vertices as the different types of serial that are available to us, or available to the cows, the edges then are the cows themselves, which follows naturally, right? So 2 to 1, this is denoted by the edge. We can like label this edge 1. 1 to 3, this is cows 3's preference. 3 to 4, this is cow 2's preference. So we can arrive at the labeling of the edges quite naturally from taking this approach. So once we have this graph, we can try to like work from the bottom up. So this is a sample input, and if I redraw the graph and if I root it at a particular node, so 2 to 1 is represented by 1. 1 to 3 is represented by 3. 3 to 4 is represented by 2. Okay, so we can kind of see that the sample input over here is like a special type of graph known as a tree. Essentially, a tree is where the edges, number of edges is equal to the number of vertices minus 1. And the nice thing about trees is that each edge in the tree has a corresponding vertex. So, for example, this edge leads to this vertex. This edge leads to this vertex. This edge leads to this vertex. Now, this is a really nice property because essentially in this problem, we're asked to determine the optimal permutations so that we minimize the number of cows that go hungry, right? But what does that mean? So the number of cows that go hungry, we can find that out by figuring out the number of edges that aren't mapped to any given vertex. So in this problem, I guess what it boils down to in graph theory then, or in the form of a graph, is that we're trying to map each edge to a given vertex. So that's essentially what the essence of the problem is then in graph theoretical terms. So if we have like another example then, another tree, we can see that no matter what sort of structure of the tree we have, we can always map an edge to a vertex. So for a tree, for the case where E equals to V minus 1, this works. Like we will always have 0 cows that go hungry. Now let's try to build upon this. So we already covered for what will happen if we have like a tree. But let's say we add like another vertex, or sorry, another edge. And this represents another cow. So edges represent cows and the vertices, they represent the cereals. So if we add like another edge, well, what does this do to our graph? And what does it do to our answer? So this creates a cycle in our graph. And what we can do is, since E equals to V in this case, so that's what we've done by adding another edge. Since E equals to V, there's exactly one cycle in the graph. And if we sort of focus on the vertex that is responsible for the additional cycle, which is 6 in this case, we can assign it to like one of the edges that it's attached to, and we can root it at that edge, or root it at that vertex, I should say. So this graph or this tree over here that I drew, we can kind of think of it as this. So this is the new edge that we've added. So 6, 5, 1. I believe this is also maps to 5, 2, 4, 3. Okay, so if we focus on this, we take this edge out. So we essentially map this edge to this serial. We can actually map the rest of the vertices to another edge. So 5 goes to this edge, 1 goes to this edge, 2 goes to this edge, 4 goes to this edge, 3 goes to this edge. And the reason for that is because if you look at the overall number of edges and overall number of vertices, we've essentially we've gone from E equals to V vertices, or E vertices and E edges, to E vertices and E minus 1 edges. Because after you remove this edge, it essentially becomes a tree. So we can sort of let this sort of logic handle it for us that we discussed earlier. So in both of these cases, let me clear the board. In both of these cases, E equals to V minus 1, and E equals to V, 0 cows will go hungry. But I guess the case that's left to be considered is E is greater than V. So in this case, if we have E edges and E is greater than V, which is the number of vertices. So we have, in this case, we actually have multiple cycles. I'll just add arrows like this. In this case, we can actually isolate a tree in the graph. And essentially, what we can do is for the edges that we didn't include, by the way, I didn't like label these, which I should have done. For the edges that we did not include in the tree, we can throw them at the end of the permutation. So 5 would go at the end, but now we can do what we did earlier. And since we isolated, I guess this is not a tree if we include 4, but we can now like do a DFS on starting from the root, and we essentially add the edge labels as we see them or as we encounter them. So 1, 6, 4, 3, 2. So this would be like a valid permutation, because essentially if we do like a DFS from the root node of the tree, all the edges match up with a corresponding vertex. So in the case of E is greater than V, what we can do, or the answer that we obtain at the end, is that the number of cows that go hungry is E minus V. So in these two cases, and if you're wondering why we haven't included the case where E is equal to V minus 2, is because that's just not, like, it's not possible. Then we'd have like a disconnected component. But for E is equal to V minus 1 and E is equal to V, we have 0 cows that go hungry. For E is greater than V, we have E minus V cows that go hungry. And so the answer for the number of cows that go hungry is the maximum of 0 and E minus V for every component that we find. So I guess the overall solution would then be, if I have like a new page. So one, we need to isolate components. Which we can, I guess, sort of do if we have a DFS or a BFS. And then two, within each of those components, we can DFS at one node, or at favorite node, I should say. And this node doesn't have to be, it doesn't have to, like, it needs to be in a particular component. So that we're working in like one of the component, and by component, I mean essentially a graph that is continuous, like it's connected by at least v-1 edges. So for each of the components, we do DFS. And after we do this, we can keep track of edge labels. And essentially this will aid us in generating the final permutation. We can probably like push this to like a vector or something. And while you're doing this, you can calculate the number of edges and the number of vertices in the component. And at the end, you just concatenate all of the subsequences, all of the edge labels into like one large string, and you output the permutation. So the overall time complexity is since it's just flood filling across the components, and we're not like doing any like additional like polynomial time or anything, the overall time complexity is actually linear. So in the problem is just O of n, I think, because n is the number of cows. So I guess that's all for like the problems. If there are any, I guess, questions, you can like put them in the chat or contact me later. But let me just stop sharing, I guess. Yeah.
Yeah, thank you, Adrish, for like giving us this lecture. It was a fantastic, in-depth, detailed walkthrough, like explain graph theories and all those stuff. It's like very good and very in-depth. I hope everyone enjoyed it and then learned something new. Even though some of these concepts may be advanced, it might come and be helpful for you in the future, and it might inspire you to like learn about these new topics that you never heard about. All right, so we had some additional problems that we have, but we're not going to walk through here. So if you're interested in doing like more questions like what has been shown, feel free to come onto the slides and check it out after the event ends. And then we provided the solutions too. And then for the questions, all you have to do is just like click on the link, and then it should take it to you. Like for example, over here. All right, and then we have we created a GitHub with all the solutions if you want to check it out for the additional problems. So yeah, you can just compare with what you did, so you can like check your work. But Adrish already showed you guys the comp dates, but yeah, just as a reminder, the US Open is very important because it's like the biggest USACO event. Going to happen in March 25th, exactly 1 month from today. That's why we had this event held on February 25th as an early prep for the US Open. And yeah, here are some of the resources that Adrish have previously mentioned. And obviously, before we end this, I wanted to say like once again, thank you for Adrish, and check out CCC if you guys are interested in like what Adrish has been talking today, and if you enjoyed Adrish lecture. And also, and if you enjoy what we're doing and want to support us with our future events, feel free to donate to us via App-In Club's website. You can just come onto the contacts and then scroll down. You can just click on this or scan this QR code, and you can donate any amount you want. But yeah, that's all optional, just based off of your own interest. And I hope you guys enjoyed the event today. And if you guys haven't already, make sure to join the App-In Club Discord server. I'll see you at the next event, and I hope you guys enjoyed